this is a lot easier.
Recording is on.
It's just a lot easier to do this and more common to do it. I mean, there's not actually much difference between us speaking here and me speaking to my students in my own institution. I mean, that's a remarkable accelerator of communication around the world.
Yes,
So,
yes, it's a good well, one of the few good benefits of this
one
pandemic.
of the few.
Yeah.
Yes.
Yeah, and yeah, it makes possible to enhance some networks that already existed. Now with this technology, we have this chance to get closer to partners that are far away, and as you said, it's not much different providing a talk in the institution and outside the institution. It's a good point.
Okay. Andre is already here, Jack. Yeah.
Oh, okay.
He's participating in my course as a student now, reinverted the roles now.
Give him lots of homework.
Yeah. A lot of papers to read. Some of these papers are yours. Well, let me say some words in Portuguese to my colleagues to introduce you about your background and your institution. Okay, I will say some words about you in Portuguese then. Bom, eu gostaria de agradecer aí o pessoal que está presente e agradecer ao Jack, principalmente, por estar aceitando esse convite de estar passando essa manhã conosco. Vou apresentar o Jack rapidamente. O Jack ele é um professor dos Estados Unidos que representa o Marine Biological Laboratório, que é uma das instituições mais tradicionais e antigas dos Estados Unidos na pesquisa de ciências marinhas. O Jack atua há mais de 30 anos nessa instituição. Ele também é professor da College, da Providence College University, também dos Estados Unidos, mas ele atua em pesquisa no MBL. O MBL não é o Movimento Brasil Livre, tá? É o Marine Biological Laboratory, que é uma das instituições mais conhecidas dos Estados Unidos, pertence à Universidade de Chicago, é uma instituição que tem alguns pesquisadores laureados até com o Prêmio Nobel. É uma instituição que se dedica como objetivo de pesquisa, tem uma prioridade no estudo de ferramentas que possam utilizar, que possam ajudar na visualização de processos biológicos, né? Então, o Jack está dentro desse contexto, né? Ele estuda comportamento animal, ele estuda como essas ferramentas de filmagem, alta velocidade e métodos de quantificação dos fluidos ao redor dos organismos podem ajudar na compreensão de vários aspectos de biologia funcional desses organismos, né? Apesar do Jack ter começado a carreira como um pesquisador biólogo tradicional, que estuda ecologia trófica e um pouco de comportamento, ele conseguiu unir vários aspectos dessa biologia funcional a áreas mais amplas, né, como oceanografia e como dinâmica de fluidos, que são coisas mais relacionadas à engenharia e à matemática, né? Ele tem uma equipe de colaboradores bem extensa, que envolve muitos engenheiros, e mais recentemente essas descobertas que os trabalhos do Jack estão trazendo têm gerado várias inspirações de biodesign, né? Então ele está começando a entrar nessa área de bioinspiração e biodesign, que eu acredito que ele vai nos contar bastante sobre isso, tá? Então eu vou passar a palavra aqui ao Jack. Obrigado a todos aí por estar presenciando esse evento, tá? So Jack, it's with you. You can share your screen and start your talk. Thank you again for accepting this invitation and to join us during this morning.
Okay, great. Thank you. Thank you, Renato. Before I start, I'd like to mention that I would like to do this to talk to you almost in a story-like way, because what I'll talk about involves biology. I'm a biologist to begin with, and a biological oceanographer. But part of what I'll describe is how by following along on a research trail, you encounter other scientists and other disciplines and may end up doing things that you never considered. And that's part of the story behind this, is how I work with engineers and physicists, even though that's not what I planned to do in the beginning. But it's been a great opportunity. So that's part of the backdrop and why I want to explain this as a story somewhat, to describe, particularly for young scientists that may end up following tracks that they have no plans to do, but that can be really beneficial. Okay, so let's see if this works fine. Can you see my the presentation, Bending Rules for Animal Propulsion?
Yes.
Yep.
All good.
Okay, great. Okay, so this is the subject that I want to talk about. And on the picture there, what it points out are both flyers, animals, birds that are flying in a fluid, air, as well as a whale tip, the rear fins of a whale. And one of the points that I'll make is, if you notice these, and just when you walk outside, notice birds and all, you notice that the structures bend, and that they bend often near the tips. And that's what I'm going to talk about. But it all started for me with jellyfish, and these are Aurelia aurita in a marine lake in Croatia. And they are the organisms that I began working with. Jellyfish, how they feed, how they swim, which are very closely related to each other. And just at the beginning, I want to point out that when we look at these animals, they're not rigid structures. They are not stiff materials. They're very flexible. This is Mystigius from Jellyfish Lake in Palau. And again, they're really great to study for a number of reasons, but one of the things I'll point out is the flexibility of the bell margin and its importance to these animals. For all of these animals, they're flexible and the margins move with particular kinematics. We know that for animals compared to vehicles, they're highly efficient. This is a figure that describes the cost of transport on the y-axis here, cost of transport in terms of energy per unit mass per distance covered as a function of the weight of the organism. And what I'll point out here is that in general, animals are more efficient than vehicles, shown here in the black dots, in terms of cost of transport, that they are capable of moving much more efficiently, energetically, in general. And among those, jellyfish, Aurelia aurita, is one of the most efficient swimmers that we're aware of. Okay, so how can that be? Well, one of the major models for swimming and propulsion involves what's called drag-based propulsion, and this is how it's thought that jellyfish swim and many organisms move. And it really centers on the fact that there are, if we take a cylinder, and we might call it a propulsor, a propulsive structure. If we take a cylinder and we move it through a fluid with its major cross-sectional area perpendicular to the fluid, so move it one way or the other, it has a lot of drag, but the force that's used to overcome that drag is what propels the organism forward, is thrust. But that drag is related to the orientation of that propulsive structure in the fluid. If it's perpendicular to it, such as this upright, it has much more drag than if it's oriented lengthwise into the flow. Okay, so that this same structure, by having this position, has a lot more drag, and by moving it and acting against that drag, a propulsor can create much more forward thrust. And that's really the mechanism that we usually think of for something as basic as cilia or anything that we call a drag-based propulsor. So on the bottom here, we see a propulsive stroke of a cylinder, of a cilia, and much of the work that has been involved with this has used ctenophore cilia. In particular, pleurobrachia is the model that's been most frequently used. And so the propulsive stroke moves in this direction, has to push against the flow, right? And that in turn creates an equal and opposite thrust on the body of the organism, right? So that it pushes the organism forward in that direction. Now, in order to maximize that push using drag, you want to have, similarly to the cylinder in the upright position, you want to have the highest amount of surface area perpendicular to the flow. So the propulsor is sort of straightened out, and then the recovery stroke to get back to the original position minimizes the surface area in the flow. So there's a bending downwards, and I'll show you examples of this with ctenophore cilia later. Okay, but basically, you're maximizing the surface area against the flow, and the way that many vehicles have done this is to use rigid cylinders and push against them, and then try in some way minimize the surface area on the return. Let's see, seem to be okay. So that brings me to a collaborative effort that I was involved with about 10 years ago that involved the idea of producing a vehicle that was as efficient as Aurelia aretha, the jellyfish. If you remember, I noted that it's a really very efficient swimmer, as efficient among animals as we know of. And that is of interest to somebody like the US Navy that would like to have devices that they could put out in the water column and swim efficiently, because although there are a number of devices, it's difficult to have autonomous vehicles that can be self-controlled and spend long periods of time out in the water. Gliders are one example, but they have a limited amount of maneuverability within particular areas. And so the idea of a vehicle that could spend longer time by utilizing limited energy supplies more efficiently was appealing. And so the Navy got involved and had a bunch of engineers, and then some biologists, including myself, Sean Colin, and John Dabiri is an engineer that we work closely with. But we worked with this group, and oh, pardon the sound on this, and built a jellyfish. And this is the jellyfish, and the energy supply is coming through this wire here. And it looks pretty much like a jellyfish, about 10 centimeters in diameter. Okay, but then I want to describe something that was involved in the background to this. These are two models of the what we call actuated muscular activities, just in engineering lingo, often called actuation. And in this case, these are the same, or vehicles with the same energy supply, but the one on the left is what we started out with. And it has no marginal flap. By the way, I just want to check. Renato, can you hear and see everything that I'm doing?
Yes, Jack, it's perfect.
Okay, great, fine. We have jellyfish here, one without a flap on the left, and one with a completely passive flap, just a silicone skirt that was added to it. Okay, we call this the no flap condition, and this the flap condition. Same energy supply, same everything except the presence of a flap. And what we found was when we measure the flow, and I'll describe briefly how we do this. But when we measure the flow, shown by the vectors here of these little arrows around the no flap condition, it's much lower than the one with the flap, even with the same amount of energy input. The white vectors here are off scale. They're faster than the velocity scale that we have here. But there's much higher velocities. And that results because velocity in the flow is inversely proportional to pressure. That is, the higher the flow rate, the lower the pressure that is associated with that fluid body. And so what we see with the no flap condition is there's velocities and low pressure where there's high velocities, but there's a much greater effect by merely attaching the passive flap to the margin of the bell. And so we see a great difference between the flap condition and the no flap. Here is the solid blue, and the fluid surrounding it moves much more rapidly with a flap. Okay, and then what we call the push versus the pull flow. The push flow is where the water is simply pushed by the structure moving through the fluid, right? And that's really what drag-based propulsion is based on, the idea that a structure is moving through the fluid, pushing against it. That creates drag, but in one direction, but in equal and opposite force that acts as thrust to push the organism through the fluid. And so we call it a push flow. On the other side of the propulsor is what's called the pull flow. That's where there's the really low pressure region. And that's where we see the highest acceleration on really the pull side, not the push side. The push side, the water's being just pushed by the propulsor, but on the pull side, there is extremely rapid flow, much more rapid, as shown here. This is the ratio of pull and push flows, that we see much higher ratio of pulling, that is this side versus pushing for the flap compared to the no flap condition. Okay, and you can actually see these in the particles that are suspended in the fluid as the animal pulse, or I call it an animal, but it's a vehicle. All right, here's one of the other things we notice. Fineness ratio is really a description of the bell shape. That is when it's contracted, its length to width is much higher, and so we call that fineness. And so here's a contracted bell versus a relaxed bell. All right. So during bell contraction, the animal moves forward, and here we have different examples. The blue ones have no flap, and the red vehicles have flaps. And there's two models, an Aurelia model with a continuous bell and a Cyanea model with lappets, that is, incisions along the bell. And the distinction that I'll make here is as the pulsation occurs, here's the periods where we see contraction of the bell. We see a movement forward, but what happens without the flap is that there's a movement forward, but then the animal sinks backwards when the bell relaxes. And then it contracts and it relaxes backwards for both models of jellyfish. Adding the flap was necessary to actually enable the vehicle to swim forward. So, so the flap made a big difference. And then we could compare these different models. Here's the Aurelia model with a flap and the Cyanea. We could compare them to the real living animals, and the ones with the flaps could move not as fast as and not as efficiently as the real animals, but at least they could move. Okay. The average normalized speed, taking into account this is the maximum speed during contraction. This is a whole cycle that includes the recovery. Those without the flap really couldn't move. And so there's something about a flap, and it doesn't have to be even actuated. That is, you don't have to put energy into it. It just can be passive that enables the vehicle to swim. Without it, it can't swim. All right. So the rest of what I'm going to talk about is why is that so? What is it about a margin that enables movement? And the work that I'll show is all based on what we call particle image velocimetry. The name tells you what it is. Particles are imaged in order to determine the velocity of the fluid. And the assumption is that when we seed the fluid with very small particles, for something like a couple of centimeter organism, we would use typically 10 micron particles. The particles are hollow glass balls that are highly reflective and close to neutrally buoyant. And so all those particles are seated in the fluid, and we illuminate that fluid with a light sheet in which the optics narrow down the beam to a millimeter or less. And what that does is really create a two-dimensional image. So then we can take pictures or images of that flow through a camera and divide up that field into many little, what we call interrogation windows. Okay. And using video with sequential images that we know the separation of each image in time, we then can divide up a spatial two-dimensional field into these interrogation windows and see how the interrogation windows change between frames. So the location of particles in one time frame may shift in the next, and from that shift, we can tell which direction the particles went and how rapidly they made that direction. We get vectors for each of these interrogation windows. Okay, and the result is you get a description of the fluid around a structure in terms of a vector field and associated measurements such as if the vectors are showing differences in direction, you get vorticity, or the rotational component to the fluid, which becomes quite important for us. And also from the vectors, we can get, because we know their velocity and we know that pressure is related to velocity, we can get pressure fields, right? And so this is for illustrating from a paper by John DeBerry in 2014, the vector fields and conversion into pressure fields for the organisms. Okay, so from pressure fields on either side of a structure, we can determine the force applied to that, because really the force is the difference in pressure on either side of the structure, right? And so this is from a paper by Lucas et al. In 2017, which measured force with transducers and PIV at the same time for a flapping foil. And so these are the differences between measurements in green here with force transducers that could measure both force and torque along the structure, and the estimates based on PIV shown in purple here. And what we find is that using the force estimates, using the PIV-based force estimates, we get a very, very reliable, non-invasive way to measure how forces change along propulsors very dynamically, because we can now watch propulsors and measure how the forces are changing through time. All right. So to summarize this approach, I mentioned we start out with particle image velocimetry. In this case, I'm showing a fish, but we can do it for any organism in a fluid. Liquid is a lot easier for us. It's more difficult with air, and our group works all in liquid. But we can convert PIV to pressure, to forces and torques along a structure. Okay, what we found doing this are some really very surprising results. So this is for jellyfish Aurelia. The red is high pressure and the blue is low pressure. And we find really along bends, this is equivalent to the pull forces that we talked about versus the push forces on the underside. As the belt contracts, it's pushing water in this direction and creating this big low pressure on this side, high pressure on this side. And I should mention that this relationship between pressure, if you've ever studied flight, one of the major mechanisms for lift and what keeps airplanes and birds in the sky is the difference of pressure on the upper side of a propulsor versus the lower side. And so what we measure then is these differences in total force between these, and we can break out the forces. So whereas drag-based propulsion has always looked at and assumed that propulsion came from thrust by pushing this bottom side, what we see is actually a much bigger low pressure on this side, and the difference across those creates a number of interesting and actually very important effects for propulsion. So on this jellyfish, we broke out the components of force. So this is that due to pull, and there's some that are at the same time we have drag, resisting forward motion, pull and push, right? And so we broke out resistive forces for pulling, for pushing, and that's what is shown here through time, plotting all those forces, because we can do, one of the advantages of this PIV-based method is that it's now possible to look at the dynamic process of motion and how forces change. And what we found is really summarized in this bottom right panel. The net pull forces, this is during contraction and this is during recovery. The net pull forces created by this low pressure on the upper side of a bend and resulting in the forces pulling it forward are actually greater than the net pushing forces. And in other words, jellyfish are really efficient, not because they're just pushing, but they're actually being pulled into this low pressure region that extends all around the bell margin. Here I'm showing in cross section, but envision this all around the bell margin. They're actually being pulled forward, and we call this suction thrust. So they've created this low pressure area using this flexible margin that helps pull them forward. So when we see these jellyfish moving along, it's important to remember they're not just pushing, but they're creating these pull forces around the bell margin. Okay, so this brings into question, how can we utilize this? So the engineers in our group said, well, okay, that's wonderful. Now you've got some data for jellyfish that says that they're being pulled along by suction thrust, but how do we design or optimize this? What are the criteria that we should use to build vehicles that can get the same advantage of biological propulsors? All right, and so, well, okay, we studied jellyfish, so we're not quite sure. And we looked at the literature, and there's actually a very extensive literature on flexible propulsive structures, right? And here's some of the results. This is from a review we did back in 2013, looking backwards. And what we found are, in general, human design propulsors, think of cars, boats, they're usually stiff, solid structures. And so by changing that, what are the results? And engineers have found both results, positive, sometimes it's negative, sometimes it's both positive and negative, right? So this is a result from, these are sort of a meta-study of more than 250 publications. Who's doing the work? Well, originally mostly biologists, but then engineers got involved, and sometimes they're combined, but primarily most of the work now is being done by engineers. What are their main approaches? Well, how many are actually empirically measuring data? Well, that's remained a relatively small proportion of the field. Most are modeling efforts, and there are some that are combined modeling, empirical, but most are models, all right? And so the models that we looked to see, well, how do our results fit with the rest of the engineering? Well, that's difficult because many of the models are based on assumptions about material composition. How stiff is the material? Is the material evenly distributed, or is it, do they vary the composition? Are there joints? How big are the joints span-wise? Are they actuated or not actuated? In other words, there are a whole range of questions and approaches to it. So it leaves us scratching our heads, and I started working with my students and asked this question, but we took a different approach. We said, well, maybe we should look at natural examples and see how they worked. So we collected videos, and this is why it was really helpful to have a number of students, videos from the web of a whole range of organisms, and we set some criteria that we only use steady state motion. That is, they had to be steady from at minimum 3 propulsor structure cycles that showed relatively stable patterns of cycling through a contraction and a recovery phase. And what we found this is a paper from Lucas 2014, that when we looked at, this is for 59 species, and we looked at where the bends occurred and how much they bent. That is, where does it occur? What we call that the flexion distance. Where does the major bend occur along the length of the propulsor from the root to the end, and how much was that bending? What we found was, although there were significant differences between species, here what are shown are each dot is an individual species. The standard errors are shown, and the gray region is the 95% confidence interval for the whole group. And we looked at birds, bats, insects, fish, cetaceans, and mollusks. What we found was that individual species are significantly different, but only within a fairly constrained range. So that flexion ratio, where they bend, is somewhere around 65% of the length from the bottom to the tip. So they're bending somewhere around, between 60 and 70% of the way. And for steady state motion, they don't bend too far. It's really only somewhere in the vicinity of about 30 degrees, okay? Whether you're a fruit fly or a whale, they have fairly similar patterns, which was remarkable to us. So that when we divided these organisms up by size, how long are they? Are they millimeter, length scale, meter scale? What we found were, wow, the flexion angle and the flexion ratio really weren't significantly different between size groups. They weren't significantly different between animals in water or air, and they weren't significantly different between any of the systematic groups. Okay, so the conclusions. The natural examples of propulsion are pretty constant across size, fluid medium, and taxon. Okay, that was astounding to us. What could be such a strong selective force that organisms from so many different groups and sizes could have converged on a relatively similar or narrowly constrained band of solutions? Again, they're not all doing everything, they're not all exactly the same, but they're within a relatively consistent band. Okay, so for us, the easiest thing then to do is to look at organisms that are small enough that we can detail the dynamics. And we took 3 different groups: ctenophores, an annelid Tomopterus, and some crustacean decapod larvae. And so here's a ctenophore. I mentioned earlier that ciliary drag-based propulsion are often use ctenophores because the fused cilia are big enough to measure. It's very hard to look at the details of cilia on, for example, Proteus, right? And you can see these cilia, they spend a lot of time bending, right? They're not rigid, stiff oars that are rowing through the fluid. Instead, they're quite flexible, and they can go either direction, right? We'll look at that in more detail. Oh, okay. This is a detail of fluid flow along a ciliary, a tein row of Pleurobrachia. And so just as in earlier I said, there's the power stroke, which has a high surface area exposed to the flow, and then there's a recovery stroke following that. But let's look at this. If we then use the PIV to get velocity fields and vorticity fields, all right? See, during the power stroke, the low pressure is in blue and high pressure is in red. We get this strong low pressure, and we'll look at it in detail here. The highest velocities, shown by the white off-scale mark, are always on the lee side. So this is beating downward, but pushing the whole body towards the top of the figure here. And the strongest velocity fields are those that are attributed to the low pressure on the lee side, like over here. Okay, we saw that for tein rows, but how about other structures like limbs for the decapod, right? And here's the decapod moving. Again, we use high-speed high-speed video with this and track the particles. And if you look at the flow fields here, again, you see they bend, right? And the highest velocities are on the lee side of the bend. These are not rigid paddles that are pushing the fluid. And what the previous work shows is really no animal propulsors that we looked at are rigid. They all bend, and they bend in very characteristic ways. Okay, and the characteristic ways show that the bend is out from the base, it's along the propulsor, and the highest velocities are on the lee side, and they're at this place where we have an intersection, sort of the interface of vorticity of different directions. At those interfaces, velocities, the rotational components of these vortices cancel out, and they complement each other or augment the linear component of velocity. So by bending, you create this region where vortices come together and accelerate the fluid at the interface of the two vortices. And when we look at these bending characteristics, where are they located? Okay, for a variety of these invertebrates, they're located around 0.6 or 60% of the way. And how much do they bend? About 27%. Let's compare that to birds and bats and everything. Bending about 0.65 and about 26%, pretty close. In other words, even at this level of cilia and appendages, these patterns seem to be holding pretty true. Okay, again, the highest velocities are on the leeward side. The pushing side has lower velocities. This is some data from a recent paper, Colin et al., 2020, that shows that and shows some of the details. And I won't really go through this except to emphasize that the peak flows are on the leeward side. And here's these limbs, and we can see these kind of peaks, whether it's an arthropod, an annelid, or a ctenophore on the leeward side, and then there's the push side as well. And when we convert these to forces, we can look at the pull forces and versus the push forces. And what we find is that this is sort of a summary of this. For ctenophores, what's the push force here? Initially, the push force is sometimes higher, say in this annelid and in the arthropods when they first start moving. But then the pull force, where you have the highest velocities on the leeward side, often contributes much higher levels of force. And the total force across the surface, the total force is comprised of both pushing and pulling, but it's actually dominated by pulling, right? So that this is the ratio of pull to push forces for these different organisms. And we see that it's always more than one. And it's often, in this case, the range of, say, 6 to 15, 3 to 7 times. The pull force is 3 to 7 times that of the push. The lowest case is in the ctenophore Bolenopsis, where it's, say, 1 to 3. But it can be as high as 30 times. On average, if we're to average all of these, it's about an order of magnitude. In other words, these limbs with these bends in that location are actually pulling the organism forward. And that pulling force is much more powerful than the pushing force that we have normally thought of, right? Which leads us to the question of, well, why 0.6 to 7 along? Why is the bend 0.6 to 0.7 way along the distance of the propulsor, and why at steady state is it only about 30%? Well, okay, here's a computational fluid dynamic model done by Eva Canso's lab with colleagues. It's not published yet, it's in press, but when they looked at, let's see if I have an example. Okay, well, I don't. When they looked at the effect on the fluid by changing the flexion angle, that is how much it bends, and where you place that bend, you can do it in different places. How does it affect the fluid? All right, so they found that this upper color region enhances the speed. So if you bend more, you can get more speed, but you have to exert more energy in the fluid to do it. So that if you want to get the maximum increase in force on or maximum impact on the fluid with the least amount of input, that is the most efficient, you would actually not want to bend as much. And there's a region designated by this solid line of overlap between efficiency and increased speed that shows a 600% increase in efficiency while also increasing speed. And these data are for the location and angle and bending angle for real animals. And so what we see is that these are for the species of fish that were considered, and it's quite a range in size, going from small to large sharks. We see that they're really in the area that maximizes efficiency. Okay, and so here's overall what we think is happening. So this is an example of just a simple bending propulsor. It's bending in this direction, just like the cilia that we saw. And that's pushing the fluid here. This is the push that has an opposite and equal effect on body motion, contributing to thrust. All right, so we see this with the PIV, that you get that push side and the higher velocities on the bent side. Those are creating vortices with rotational motion that focus the intersection point and the highest velocities right at the intersection where the bend is. Okay, and that creates high pressure on one side and low pressure on the other. That, yes, we get drag-based propulsion pushing the organism, but suction-based is actually, for all the cases we've measured, much stronger. Okay, and we think that is why we have this convergence in design between such phylogenetically different groups. And we expect that that is the strong selective force powering this whole system. And I think I'll stop there because that's where we're at now. We're now, we have developed the empirical methods to test this, and we now have this hypothesis. I should note, it's not been really incorporated into designed vehicles at this point, because we're still demonstrating that it exists. The use of natural models is, from our perspective, clearly advantageous, but it takes a while to penetrate the engineering literature. Okay, so I'll thank you for listening to that and answer any questions you might have.
Hi, Jack. I thank you for your wonderful talk, for your wonderful image you share with us. And I would like to open to everyone who have any question or curiosity or comment on your talk. You can do it in Portuguese as well. And then I translate to Jack. Oh, Eduardo already asked something. Yeah.
Great.
Go ahead, Eduardo.
Thank you, Jack, for this very interesting talk and for the research you and your group are doing. My question is, when you did that survey of analyzing how many studies had the positive thrust and negative thrust, I noticed that there were some with either negative and both positive and negative. What does that mean? What does a negative thrust mean in this case?
Okay, really what that meant was an increase in flexibility yielded lower performance in terms of thrust than a stiff, than a comparatively stiff. So some, it's frequent in some of those studies to vary stiffness in the propulsor, the material. So for high acceleration, often a pretty stiff material is favorable. And so they could get you could have results that spanned negative to positive. That is, if you get a really flexible material, it just kind of waves back and forth and doesn't provide enough enough stiffness to even give you push, right? And so by varying stiffness along the gradient, you can have both negative and positive results in the same experiment. And I think that's how that, those are the ones that I recall like that, which to us makes sense that that could be the case.
Okay, yeah, and my last question is, when you, at the end of your presentation, you did a kind of synthesis of these relationships. Have you ever? I'm not sure if it's implicit in that result, but have you ever looked at the outliers and see what makes the outliers efficient in their evolution?
Yeah, no, I think that's a great question, because often the outliers are what give you the greatest insight because of their deviation from the norm. And I'm trying to think of outliers that we've looked at. We've started to look at acceleration. For example, all of our work, or at least the Lucas et al. Comparison of multiple species, was based on steady state motion. That is, a regular cyclic motion, as opposed to a sudden or abrupt change in motion. And what we find is that often the bending is more pronounced. That is, it involves more of the propulsor, and the angle of bending is greater. So we've just have started down the path of trying to understand that. But that's as far as we've gotten sort of with outliers yet. What are causing deviations from our standard? And it's very clear that sudden accelerations often involve deviations from our pattern, and we want to understand why. But that's sort of where we are, because one element that I'll add is, you might note that all of those publications that are mentioned are within the last 6-7 years. These methods are all that we can look at in detail. The dynamics of these processes are pretty recent work, and the one that that we looked and demonstrated the prevalence of suction thrust and its dominance, not just for one or two species, but actually for quite diverse species, is a 2020. So we've been really focused on establishing the basis, and we now have to look at what are the conditions that cause deviation, and what do those deviations show us about the advantages or disadvantages.
Fine, thank you.
Sure.
Yeah, I suppose understand and explain outliers is much more difficult than the normal pattern, right? And congratulations for this very, very interesting work. It's really obviously very applicable to engineering. Thank you.
Yeah, thanks. Well, and it's the engineers are, well, first, they can do brilliant work. But one of the things that we've recognized is that it's very rare for engineers to have any biological training. So you often start from very different initial understandings of things. And it's one of the advantages of a cross-disciplinary exercise that you have to go back to the very, very basics. Each of us, they have to treat us like idiots, and we have to treat them like idiots, and that helps to start from the beginning and build.
Pessoal, se vocês tiverem alguma pergunta que queiram fazer, um comentário, podem, sintam-se à vontade aí, fazer em português também, e aí eu posso traduzir ao Jack. Bom, eu vou fazer uma pergunta. Hey, Jack, from the beginning of your talk, you showed some the robot that was developed after your research. And then one thing that called my attention is the battery. It's in the upper side of the animal. And then I start thinking about this question about the energy that these vehicles would consume. And also that graph that you showed that the jellyfish is the least, the most efficient animal in terms of energy expenditures. So how these engineers that are intending to develop robots, how they think about the energy input that these vehicles will need? Is there any ways to? It seems that a vehicle would be very limited by the energy input. How is there any solution for this problem?
Yeah. I think that's a great question, and the focus of a project that we've been working on with some other engineers in a different group, also funded by the Navy, and their thought was, in the world of material engineering, there are actuators or artificial muscles that can be extremely powerful, and using nanotubular designs and carbon fibers can be very efficient. And so it sounded like a brilliant idea to take this really efficient animal design and use the cutting edge actuators to power it, and then we should be able to build like a really new type of vehicle. Okay, unfortunately, after a couple of years, we really haven't made that much progress because carbon nanotubule actuators that we were working with, they are extremely powerful, but they're nano yarns that are a mile of them you can fit in a gram of material. And so it takes a long time and is very expensive to build these. And so although we have a lot of the parts to build really efficient structures, we're still very energy limited in terms of actually doing it. And there are strong possibilities for the future, but what we've found is difficult. In short, that project has been pretty much of a failure. We just weren't able to convert the newest technologies on the scale that's necessary to operate these types of vehicles. So at present, the vehicles are still very energy demanding because the artificial muscles, we don't appreciate how efficient our living systems are. The artificial muscles that are used to drive, for example, the vehicles that I showed are very energy demanding. And so, although the design of the vehicle is efficient, the actuators themselves are very inefficient compared to living systems. And right now, we haven't resolved that.
Okay. Well, another question I have maybe on the same topic is that I started to study and to look for this new research on jellyfish, and then I saw a study by John Dabiri that puts a peacemaker inside the jellyfish that makes the jellyfish pulse in higher frequency, and
Yes.
he could like control the at least the velocity that the animal moves. And if the animal, one of the things that they discuss is that if the animals could eat, they could supply themselves with the energy, and perhaps it's another solution for this case, because I see a lot of applications of animals that could be controlled and carry sensors or things that could measure oceanographic parameters in the water. And
Right.
then I just was wondering about possibilities that is.
Yeah. Okay. And so, one of the thoughts there is that if you could, instead of trying to invent new materials that we don't have yet and coordinate them, how about if we were to use actual animals? And jellyfish are a good example for this because, they have a higher potential for this because the contraction of the bell occurs via a nerve net. That is, there are pacemakers in the rhopalia around the bell margin that one of them sends out a signal and it moves through the net and causes muscular contraction. And then there's a refractory period after that contraction where none of the pacemakers are sending signals and the bell recovers. And then whichever pacemaker fires next causes another contraction. All right. And so Nicole Zhu, working with John, essentially hijacked that sensory system by putting in these little electrodes that had signals of similar magnitude to the pacemakers in the rhopalia, but changing the frequency. That she's essentially just stepped in to the existing system and changed the frequency so that the refractory period wasn't as long. The downside of that is that the refractory period or the recovery period for jellyfish is actually an important part of their hydrodynamic system for harvesting energy from the vortices. While they're sitting there, not doing anything, the vortices that they created during the power stroke and the recovery are sitting under their bell, rotating, and there's a place where opposite spin vortices come together, creating a push up on the underside of the bell. So the jellyfish is not actually using muscular energy, but it's harvesting fluid energy that it generated during the contraction cycle. If you be faster, you don't harvest that energy, so you lose efficiency, but you can go faster. So those are some of it's not as if the natural cycle is less effective. it's more effective at harvesting energy from the fluid, but it can be sped up if you want to move the vehicle faster. And that's what Nicole did with that. It does have the advantage if you want to use them as sensors that they can feed and you don't have to keep supplying them energy all the time. And they can also have a limited ability to heal wounds and things that vehicles don't have. So I think that's the argument for trying to develop that line of thought. It has both advantages and disadvantages because you're probably going to decrease the energetic efficiency of the organism by doing that.
Okay. And also the organism is still available for being food of a turtle, for example. And
yes.
You may lose the organism in nature.
Yeah, you may lose the whole thing and in the process. But yeah, that's one of the design considerations actually we had with artificial jellyfish. What if the artificial jellyfish looks like a jellyfish and turtles and not just turtles, there's lots of fish that eat jellyfish or take a bite out of them. What if they take a bite out of this really expensive device and then get sick? You know, it's so these are these are considerations, but since we have no really good vehicles yet like that, it hasn't been a problem that has been important yet. It probably will be, but not yet.
Okay. Let me ask if the students have anything to ask you. Pessoal, podem falar aí, não fiquem tímidos aí, eu acho que é bom aproveitar essas oportunidades aí. Não sei se vocês têm algo de curioso ou de alguma dúvida que tenha ficado em relação à palestra ou em relação aos assuntos que a gente tem tratado na disciplina também. Acho que agora é o momento aí que vocês quiserem comentar, fiquem à vontade. Podem. Senão eu vou fazer uma outra pergunta.
So, if a turtle eats this device, it would be like $100 of wasted, probably.
Thousands and thousands. Yes.
Here in Brazil, it would be like, I think it's impossible, but so I have a question about, actually you raised up this question when you showed where it's how much it would be the angle of the bending surface and the position that would be like in 60% of the structure. So you have shown that both like air animals or water animals almost bend, and where they bend almost in the same place, right? So you raised up, why is that? It's a little bit foggy in my head still, because what could it be like? It's the performance that for the propulsive structure for be efficient, it must be that way. Or it's too confused.
Yeah, I mean, it's from what we know now. It is really the position of how you press these opposite spin vortices together, because that's where you get an acceleration at the interface, right? So where you position them on the propulsor is also important for the operation of the propulsor, right? It seems that you can, if you position it closer to the body, it's harder to get the right angle, right? So say you want to have a 30% angle. If you position it closer to the body, it can be harder because you've got more of the propulsor extending beyond that bend. We're not really sure of all the limitations. For example, we do see that the propulsor position and extent changes during rapid accelerations. So organisms can do that, and there's some reason to do it, but we're not sure why yet. There's some things, there's many things that we don't know. We know the physical mechanism that underlies it. We know the empirical patterns for their application. We don't know how much you can vary those patterns and still have it be successful. And sort of very fundamentally, we don't know if this is completely limited to inertial regimes. That is, we see it work for cilia and ctenophores, but those are fused cilia, and they're pretty big, and they operate at Reynolds numbers of about 50. What happens with smaller cilia on the size scale of ciliates? We don't know the answers to any of those questions yet. So I would say we have the basic outline, but a lot of the details that determine variability are not determined. We don't know how they work yet.
Okay, got it. In order to the vortex form, it must be in inertial fluid regimes, right?
Well, yeah, because we usually think you can't. Vortices are really an inertial phenomena, although there are viscous vortices that form. You can still have rotational fluid in just a shear fluid regime. We don't know if that matters, but we're used to thinking of inertial vortices, and that's where we see very clear evidence at this point. We don't know if that extends into lower Reynolds number regimes or where the boundaries are. We don't expect it to, truthfully. But we can't rule it out for viscous vortex structure until we actually experiment with it. That work hasn't been done.
Okay, really nice. I think what's beautiful for me, it's like you came up with all these rules about the performance and how the structure bends and how it propelled the animal. But when you think the real animal, I think there is like a willing or the animal can manipulate all this its structure to choose what he wants. Like, I want more speed, or I want to enhance my performance through these push and pull movements that you show. I think that's really that's make more complex and really nice as well.
Well, yeah, thank you. Yeah, definitely we've shown a very simplified version, and really it's based on primarily steady state, and we're just looking at non-steady state conditions. But the organisms are always going to be more sophisticated than our simple, the simplifications that we generate because we need simple systems to understand. Yeah.
Okay. I have another question, Jack.
Okay.
In a previous class, I was teaching them about drag-based propulsion, and then I showed a schematic drawing about how drags operate, and there's a large arrow about a large vector about the drag, about the higher pressure upstream, and smaller vector downstream the movement, and then you show the opposite, like big arrow showing the low pressure fields and a smaller arrow showing the high pressure fields. So yeah, I think I will not throw away my books because they're expensive, but I will show them as example that things change on science, and you are showing us a front line of your discoveries, and it's wonderful. And more than that, I showed the students only two examples of this suction-based propulsion that came from the study by Gamel 2014. But
Right.
it seems that you are maybe finding that this is a general rule that many of the organisms pull themselves through the water. This is intriguing, very intriguing for me.
Oh yeah, thanks. Yes, I would agree that is where we're heading right now. What we found originally in that demo paper, I don't know, it was 2014 or 16. I'm not sure which, but we used lampreys and Aurelia, two quite different animals. But what we're finding is that it's true for a variety of organisms, and that's why we hypothesize at this point that that's the driving evolutionary force for the empirical measurement. When we measured all those bending patterns by animals, we had no mechanistic explanation. That data just arose because it's a descriptive study. Engineers said, where do we put the bend and how much do we bend? And we measured how animals do it and said that's what it was. But we didn't really understand why that's so. We now have a mechanism, and we have computational fluid dynamic models that explain that mechanism as a trade-off between efficiency and proficiency, or how rapidly you want to swim, but how efficiently you want to do it. But that's all pretty new. So I think we don't have enough testing of that yet. We need to challenge it more, I think.
Yeah, of course. And also you showed a graph when you compare the model, the outcomes of a model in a curve, and then the empirical measured data, and they fit really close. But this could be interpreted as a reason why using only models, because they are not expensive than doing experiments. So how can we discuss this issue?
Yeah, I think that's I think that's interesting, and I'll admit my bias. I don't trust models. I don't trust any models.
Yeah.
I like to see, clearly I want to study and see the actual fluid measurements, and I want to see all those things bias me towards empirical measurements. Now that model that you mentioned and that is part of the study that's coming out, it's in press now, but it's only one model among many models. Other models show very different results. So that's part of why I don't trust models, because they rely upon the assumptions. And if you don't have any idea about suction thrust, it doesn't show up in your model, and therefore your model doesn't support it because it's not among your assumptions. And so I would say that the fact that we have a model that agrees with our empirical results probably reflects modelers that took into consideration thoughts from our design. But does that mean all modeling is adequate and forget about it? Because we've had lots of models for a long time, and they haven't explained that phenomena. So I would say yes, models can be great, and I hope modelers won't throw bricks at me or anything, but I think that they're extremely useful for formalizing assumptions and views of phenomena. They force, to build that model, they have to say, this is how it works, we're going to make these assumptions. That's a very valuable part of the process. But how they do that determines the outcome of the model.
Ok. Em português, não. Pessoal, alguém tem uma pergunta, algum comentário? Pode fazer em português também, eu traduzo. Se alguém tiver aí, podem fazer, não se sintam inibidos aí. Eu acho que talvez até tenha, mas... Bom, eu vou fazer mais uma pergunta aí, o Jack, então. Jack, now talking more specifically on the jellyfish, well, we all are aware about this hypothesis that the jellyfish blooms are increasing and perhaps the jellies are taking over in the oceans when other impacts may occur. Do you have anything that you think on the biomechanic perspective that facilitates the jellyfish to be so dominant in their environments?
I don't really, because it's not something that I know particularly about, except that one thing that influences my thought about this is some work that Eric Dusen did back in the early 2000s, showing the mesoglia as essentially a carbon storage, an oxygen storage area in the jellyfish. For me, I'm well aware of the mesoglia as a antagonizing element to muscular contraction. That is, contraction occurs in one direction, and then the mesoglia antagonizes it for recovery. Or acts in, when I say antagonizes, acts in an opposite direction. I think that's one of the elements that they can store oxygen and then draw it down during low oxygen periods, is one of the benefits that being a jelly animal has in low oxygen environments for these animals. Otherwise, and the fact that they take relatively low amounts of food to build pretty big bodies is also I think an asset in some of those conditions. But the whole question about whether jellyfish are taking over or occupying niches that are being either abandoned or removed by, say, overfishing, is one that I think is a developing one and is interesting, but I'm not sure what to say about. I'm not sure I believe everything that I read, but I can understand how it might be a phenomenon that will be important. I'm very influenced by some work in the Adriatic Sea that showed that hydromedusae diversity was declining for quite a while because of hypoxia affecting the pulp stage of the life cycle. And so that conflicts somewhat with the picture of jellyfish taking over. And it strikes me that some jellyfish may be benefiting, but we may be losing diversity in a lot of other groups.
Yeah. Well, you mean that we have also opportunistic jellyfish that can benefit from this change in the environment, and also many other species that may not be benefited by this.
Exactly. I mean, I suspect that it's a much more nuanced picture than just jellyfish taking over. It's almost when you have environmental disruption, some species may be favored, and you may have a net decline in diversity, but an increase in the absolute biomass of those species that are favored. So I can see that happening, but that's a more nuanced picture of the idea that jellyfish are just taking over. It may be just some species of jellyfish are thriving. I suspect that's more the case.
Okay, excellent. Well, any other questions for Jack? Well, you guys are shy today.
Oh, that's
okay. No problem.
Well, also I appreciate that. I appreciate you letting me speak to you in my language, because unfortunately I can't speak in yours. But I'm grateful for that. So.
Yeah. Well, I'm sure that everyone could catch your main message, because your English is pretty clear. It's very easy for us to understand. And thank you again for accepting this invitation from our university, from my course. And it was wonderful to have you here, bringing all these frontline outcomes of your research for us, and sharing all your knowledge and expertise in many things. Well, it's just amazing to have you here, and thank you again. And
okay.
I think everyone is very happy about having such a good talk today, this morning.
Great. Well, thank you, everyone.
Okay, thank you.
Okay.
See you, Jack. Pessoal, então acho que a gente volta às 2 horas, né? Hoje tem a reposição da aula, e aí voltamos lá, então. Beleza? Tchau. I will close this window. Tchau.